In the last video, I stated and proved Shearer's lemma, and as promised, in this one, I'm going to give a couple of applications of the lemma. But I think I'll start by just reminding you what the lemma said. So it said that if we've got a random variable x, which equals, my pen's gone a bit thin, which equals x1 up to xn, and if we have a random subset S of n, and for all I, probability that I belongs to S is greater than or equal to mu, then we can say that mu times the entropy of X is at most the average over all S of the entropy of XS, where XS is the sort of tuple of xi's for which I belongs to S. And well, let's have a straight away an example, a reasonably simple example of how this is applied. So let's ask ourselves the following question. We have a graph G. It has M edges. How many triangles can G have? A natural, when you think about it, you sort of feel that you want as many, you want each edge somehow to contribute as much as possible and with as many other edges as possible. So after a little bit of thought, it seems a pretty natural thing to conjecture that the best you can do would be to choose a complete graph with M edges. Let's just assume for convenience that M happens to equal N, choose 2 for some N. So let's just see what happens in the case of the complete graph. So supposing G equals Kn, then we'd have that the number of triangles is n choose 6, sorry, n choose 3, which is roughly n cubed over 6, and the number of edges is n choose 2, which is roughly n squared over 2. So if we write t for the number of triangles and m for the number of edges, we get that t is roughly 2e, that gives us n squared. So I'll turn it into an n cubed by raising to the power 3 over 2, and then turn it into the triangles by dividing by 6. And what we're actually going to prove is that this is more or less the right value. We're going to prove that t is less than or equal to a sixth times 2e to the 3 over 2. In fact, you can go further than this. There's a theorem called the Kruskal-Casimir theorem, which implies reasonably easily that a complete graph really would be the best. But this entropy argument is going to give this bound, which is pretty good. So let's see how to do it. So this is going to be an instance where we will basically choose a random triangle, but how are we going to think about that random triangle? We'll think about it as follows. So let x equal x1, x2, x3 be so it's a random triangle, but I'm going to think of it as a random set or random triple, so it's ordered, of vertices that form a triangle. Chosen uniformly. So the number of such triples, so let's let T be the number of triangles. So then the number of such triples is the number of triangles times the number of ways we can order each triangle. So it's 6t. We can order the vertices of the triangle in 6 ways. So we get that h of x equals log of 6t. Again, log to the base 2. But let's, we're not going to use that at the moment. We're just going to think about h of x. And we'll use Shearer's lemma. So by Shearer's lemma, we'll just use it straight away. We have that, right, so I've got to decide what my random S is. Let's go back up to here. So S is a random subset of 1 up to n. N is 3 in this case. What I'm going to choose for S, not surprisingly because I want to relate it to edges, I'm going to choose all pairs, or a random pair of numbers from 1, 2, 3. So let's say with S, a random subset of 1, 2, 3, chosen uniformly, of size 2. We get that, so what probability has an element of 1, 2, 3 got of lying in this random set of size 2? Obviously 2/3. So mu in this case is going to be 2/3. So I'll have that 2/3 times the entropy of x is less than or equal to, well, I'll write it out in full. So it's going to be the average over S. And so S is 1, 2, 2, 3, or 1, 3 with equal probability. So we'll get a third h of x1, x2 plus h of x2, x3 plus h of x1, x3. And let's think a little bit further. So at least one of these 3 must be at least as big as 2/3 h of x. And we'll assume that it's x1, x2. So without loss of generality, 2/3 h of x is less than or equal to h of x1, x2. And h of x1, x2, well, what do we know about x1, x2? We know that it is an edge because it's part of a triangle. So this is certainly at most h of, let's call it w, where, I'll call it e, there's no reason not to, where e is a random pair, this time I mean uniform random pair, sort of x1, x2, that forms an edge of G. But here, I mean, it's an ordered pair, so it forms an edge by forgetting the ordering. So, so that tells us that, so here I've used maximality. So x1, x2 is not necessarily uniformly distributed over all ordered pairs that form edges, but by maximality, it's at most the entropy of a uniformly chosen such pair. And we know exactly what that is. H of E is log of 2m. So why is it log of 2m? Because there are m edges, and then each edge, you can order its vertices in one of 2 ways. And so we get that, just plugging in this log 6t for h of x, we get that log of 6t, I'll now take the 2/3 over to the other side, is 3/2 log of 2m, it's more or less game over here. So 6t equals 2m to the 3 over 2, and divide both sides by 6. T equals a 6. 2m to the 3 over 2, and let's just quickly go and check. Oh, I called it E. I meant to call it M, but it's the same bound. So this one had E edges, and this one down here has M edges. So that's finished the proof of that bound. And now the second result that I want to prove concerns a very nice concept and a beautiful problem that was open for a long time. And it's the following. Supposing we take curly G to be a family of graphs with vertex set 1 up to n. And we'll say that, so this is going to be, we're going to impose a property on curly G that is a rather nice generalization of a property that we considered much earlier on in the course. We'll say that curly G is triangle intersecting if G1 intersect G2 contains a triangle. For any G1, G2 in curly G. So there are all sorts of results about different sort of variants of intersecting families. So we just considered the case of families that are intersecting in the sense that they have a non-empty intersection, but you can also consider, for example, and this has been looked at a lot, families where you ask for any two sets in the family to intersect in a set of size at least R, for example. That would be called an R-intersecting family. But here we're doing something more. We're actually insisting that the intersection isn't just large, but has some sort of structure. In this particular case, is a triangle. And so it's very natural then to ask, how large can a triangle intersecting family of graphs be? And looking at what happens for intersecting families, well, let's just write this. How large can triangle intersecting family be? So one construction take all graphs that contain some fixed triangle. So how large is that? Well, there'll be 3 edges in that triangle, all of which, if you don't impose any conditions, have 2 options, either to be in the graph or not to be in the graph. So there are 8 options for the 3 edges, but we're insisting that they're all in the graph. So we've divided a number of total options for the graph by 8. So then we get that curly G has size, the total number of graphs with vertex set n, which is 2 to the n choose 2, divided by 8. I could write it as 2 to the n choose 2 minus 3, of course. And for a long time, it was conjectured that this was best possible, but nobody was able to find a proof. The fact that they're triangle intersecting, that implies immediately that it's an intersecting family. So we immediately get an upper bound of 2 to the n choose 2 minus 1. Perhaps I'm going to relent, actually. I'm going to call it 2 to the n of n choose 2 minus 3. Of course, it's the same. I'm going to use entropy. This is not my argument, by the way, but I'm going to use entropy to prove a bound of 2 to the n choose 2 minus 2. So it's going to improve on the easy bound by a factor of 2, but it doesn't solve this conjecture. However, I should mention that pretty recently, in the last probably 6 or 7 years. I can't quite remember the date that it was done. David Ellis, Yuval Filmus, and Ehud Friedgut did solve the conjecture, and this is indeed true that it's true that this is an upper bound. So you can get this, and this is in fact the best you can do. And that proof is very, very different from the proof I'm going to show you. It uses quite a lot of representation theory and things like that. But that's a completely different course. I can't, I'm afraid, explain where representation theory would come into a problem like this. So let us go ahead and prove this intermediate bound. So each edge, E, has a possibility of being in a graph or not in a graph. Now, I'm going to say okay, so first of all, let curly G be a triangle intersecting family. We're going to do the obvious thing. We're going to try and get an upper bound for the entropy of curly G. Well, the obvious thing, given that we know that we're going to be using entropy, because I've told you. So we're going to try and work out an upper bound for the entropy of G, and that'll give us an upper bound for the cardinality of G. We'll just have to raise the entropy to the power 2. I beg your pardon, we have to raise 2 to the power the entropy. So we're going to think of curly G. So our random variable, sorry, that's the family. So we'll let X be a random element of G, which is just a graph chosen uniformly. So I'm sure you understood what I was trying to say before, but what I meant to say, I mean, the actual words I should have said is, it'll be 2 to the entropy of X that will give us the cardinality of G, because it's chosen uniformly. So we want an upper bound for the entropy of X. Moreover, we want that upper bound to imply that the cardinality of G is at most 2 to the n over 2 minus n choose 2 minus 2. Now, we're going to think of X. We want to apply Shearer's lemma, so we want to think of X as being a random variable that's made out of a whole lot of other random variables. And the way we do that is we'll think of X as, I'll write it like this, XE, where E is in N2. So each E is a possible edge. It's a pair of elements of 1 to n, and XE will be 1 if E is an edge of the random element of G, and 0 if E is not an edge of the random element of G. So X is just a random graph chosen uniformly from the family of graphs G. XE is telling us whether the potential edge E is actually an edge in the graph that we've chosen or not. And now we want to apply Shearer's lemma, and this we're going to do in a much more interesting way than just picking all subsets of n choose 2 of some given size. So what we'll do is as follows. So let R be a random subset of n, not n choose 2, and let S equal the complement of R. And for each, for a given graph G in curly G, let's write GR to be G intersect the complete graph on R union G intersect the complete graph on S. So let me just draw a little picture. We have some graph like this, bunch of edges. We randomly partition the vertices into two parts, and we take all the edges that live inside one of the two parts, and we throw away all the edges that go across. We don't have the ones that go across. Okay, and so now let's just notice that each E, actually that's not quite what I wanted to say. But I'll leave it as it is. But I want to say, I want another definition. So I'm going to define, let's come out another letter. So let's WR. Let that be the graph R choose 2 union S choose 2. So GR just equals G intersect WR. So I want to make a couple of observations. So each E has probability 1/2 of belonging to WR. That's because it belongs to WR. This is just a random red-blue coloring. We can think of it like that. We color some of the vertices red and some of the vertices blue. So an edge belongs to WR if and only if its two vertices have the same color. And clearly that happens with probability 1/2. So that tells us that by Shearer's lemma, a 1/2 entropy of X is the average over all R of, sorry, it's less than or equal to the average over all R of the entropy of X, which is just a graph, intersect GR. Now remember, X is not just some fixed graph. It's important to be clear about that. X is a random graph chosen from the family curly G. So let's think about what let's think about what the entropy of this could be. So what can we say about the set of X intersect GR such that X, I've called it GR, which is not what I wanted to say. I'm going to say WR. I had previously intended to call it GR, which is why I've done that. So, or we could have called this just XR. So what can we say about the family of graphs X intersect WR such that X belongs to curly G? So far notice that we've not used the fact that curly G is triangle intersecting, but now we're just about to do that. So I've got a triangle intersecting family, and so that tells me that if G1 and G2 belong to curly G, then G1 intersect G2 intersect WR is not empty. Let's just see why that is. It's because G1 intersect G2 contains a triangle, and I've got my partition into R and S. No matter how I draw a triangle, by the pigeonhole principle, there must be at least two vertices on one side, and so I've got an edge that I don't throw away. I'm left with an edge. So that is an intersecting family. And what else can we say? We can say that also that each X intersect WR is a subset of WR. So just going from this observation here, that implies, by what we know from way back in the course, we know that an intersecting family contains at most half the set. In fact, I'll just remind you of the proof. It can't contain both a set and its complement, so it contains at most half the sets. So that implies that that the entropy of, well, let's just do it in two steps. So this family has size at most 2 to the number of edges in WR divided by 2. So that tells us that the entropy of X intersect WR, which was the thing we were interested in, is at most the log of that, which is WR minus 1. And remember that each edge has a probability of half of belonging to WR. So when I take the expectation over R, so that implies that the average over R of H of X intersect WR is less than or equal to the average over R of WR minus 1. And the average over R of WR is a half n choose 2 minus 1, because each E has a probability of half of belonging to WR. It's got a half, again, it's that same thing. It's got a probability of half that its two vertices have the same color, so to speak. Now, what was that an upper bound for? Just that was an upper bound for half the entropy of X. So we've got that, that tells us that the entropy of X is less than or equal to n choose 2 minus 2, and we're home and dry. Therefore, the size of G is at most 2 to the n choose 2 minus 2, which was the bound that we were hoping to prove. Let's put a little square at the end because I feel sort of satisfied by that. So let's just think a little bit more about that. There's something, it's not exactly the same as the proof of Kruskal-Castaner. Sorry, let me Kruskal-Castaner. I mean Castaner's proof of the Erdős-Coe-Radó theorem, but there's a certain sort of similarity with it. So there with the Erdős-Coe-Radó theorem, we did a kind of averaging argument, and we said that we'll sort of restrict ourselves to a small bit of what's happening and look in that small bit and get an upper bound in there and then do a big averaging argument. Here we're not exactly doing that, but we're sort of doing that. What we're saying is that we sort of restricted our attention to the edges that lay inside, either inside R or inside S, and got an upper bound for what happened there. But here we're not actually if we're looking at families of graphs, the graphs themselves we restrict to these, but the families of graphs we're not restricting to these sets. And actually, if you think about it a bit, what we're doing is a bit more like a projection than an intersection with a subset. We're sort of taking a random projection. And actually, that's a quite, that's not just a sort of, that we really are, in a certain sense, taking random projections. And there's a strong connection, and you'll see it on the example sheet, between Shearer's lemma and something called the Loomis-Whitney inequality, which you may have heard of, which says if you've got a nice set in R to the n, and you project it in various different directions, you can get a bound on the size of the set in terms of the sizes of the projections. But with that little remark, I think I've finished, and actually that finishes the section on entropy. And so starting with the next video, we'll have a very, very different topic.